Hey everyone, today we're going to find the area under the curve for these two functions with the specified area that I tried to color with that marker. So for example 1, we're going to look for the area under the curve for the function described by y is equal to x times the square root of x squared plus 1 between the values of x equals 0 and x equal to 2. Right? To do that, we are going to integrate. Right? And so we're going to use the definite integral. We're going to say the area is going to be the definite integral from 0 to 2 of that function here. So of x times square root of x squared plus 1 dx, right? And that value is going to be the area bounded by the x-axis and this curve, right? And so to solve this integral, we are going to use a u substitution. We're going to say let u be. Now, again, with these u substitutions, we're looking for a convenient expression for u where du is going to be something really convenient to kind of catch everything we need inside this integrand. And so what I suggest is to let your u be x squared plus 1. What that'll mean is that du is going to be the derivative of x squared plus 1 is 2x and then dx, right? And so that means that this x dx is almost this. So if we divide both sides by 2, that means that du over 2 is equal to x dx, which means we can replace x dx with 1/2 of du. And then we have the square root of just u. And so with a change of variables, we can make this integral be the 1/2, because d over 2, that's the same as like 1/2 du, right? So that's 1/2 the integral. Now, if we're going to change from the variable x to the variable u, we should also change our limits of integration. So if u is x squared plus 1, if x is 0, then u is 0 squared plus 1, which is 1. And if x is 2, then 2 squared plus 1 is 5. So let's say from u values of 1 to 5, we have 1/2 the integral of the square root of u du, right? And this we can integrate pretty quickly. This is u the 1/2, right? And so we're going to raise the exponent by 1. 1/2 plus 1 is 3/2. So we'll have 1/2 times u to the 3 over 2, and then divide by 3 over 2, which means 2/3, like so. And this is evaluated from u is equal to 1 to 5. And we could de-substitute and go back to x and go back to the x limits of integration of 0 and 2, or we can just go ahead and evaluate this as it is. I'll show you both ways. In fact, that's probably worth our time. So here, the 2's are going to cancel, so we'll have 1/3. Let's leave that out front. So we'll have, you know what? Well, yeah, okay. That'll work out all the same. So we'll plug in 5 first. So we'll have 5 to the 3 over 2. The 1/3 is outside, and then minus 1 to the 3 over 2. And we know that 1 to the 3 over 2 is just 1. And so our final answer would be 1/3, 5 to the 3 over 2 minus 1. If you want to see that going back to the variable x would give us the exact same answer in the end, let's go ahead and do that. So we would have 1/2 times 2/3 u to the 3 over 2. So we would again have 1/3. And now let's make u, again, x squared plus 1. So we'll have x squared plus 1 to the 3 over 2. But now let's go back to the limits of integration that were on x. And so from 0 to 2. And that would mean the 1/3 can stay outside. Let's plug in 2 first. 2 squared is 4. 4 plus 1 is, right, 5 to the 3 over 2. Minus, if we plug in 0 in for x, 0 squared plus 1 is 1. So 1 to to the 3 over 2, which is the exact same result we found the first time. And so again, we get an area that is 1/3 5 to the 3 over 2 minus 1. Okay, that is this area. So that took up a lot of space. I'll try to do E down here. So I've talked a lot about the area stuff, so we'll just get right down to it. So the area in here, area is going to be the integral from 1 to E of 1 over x square root of ln x dx. And we're once again going to solve this with a u substitution. So what I'll suggest is let's let u be, again, we have to pick a u where the du will be convenient, right? And so I even suggest writing both down so you can really picture how both are going to interact with one another. That's really the whole game with these u substitutions. And so I suggest making u ln x, because then du is going to be 1 over x dx, which is 1 over x, and that'll be 1 over x and dx, and that's a lot to take care of. And so let's go ahead and do that. So we'll make this be the integral from, now again, sometimes we just kind of like ignore the limits of integration, but let's be proper here. So if x is 1 and u is ln x, ln of 1 is 0, so u would be 0. And if u is ln x, when x is e, ln of e is 1. So we'll change those to 0 and 1 of 1 over x dx is just du. And then we'll have 1 over the square root of u, right? And now, because you're familiar with exponents, you know that this is the integral from 0 to 1 of u to the negative 1/2 du, right? And we can integrate that. So that is, go up by 1, the exponent goes up by 1, so that is u to the positive 1/2, and then we divide by 1/2, which is the same as multiplying by 2, from 0 to 1. And now, those are such nice values, let's just plug those in. So that'll be 2 times 1 to the 1/2 minus 0 to the 1/2, right? And that is just 2, right? 1 minus 0 is 1, 2 times 1 is 2. And so our area under the curve bound by the x values 1 and e of this function, and the x-axis is exactly 2 units. That's a kind of cool result. Not really what I expected. I expected it to be some messy irrational number, but we get a really nice value of 2. And so again, with these u substitutions, just keep that in mind. Write u, write du, so you can really see how they interact. And so you want to make sure they grab everything inside your integral, change your variables, and then go ahead and evaluate your areas under the curve. So I hope that helps, and thanks for watching.